Going to start, ma'am.
Going to start. Okay, when is the deadline for your assignments? I
Tomorrow.
be yeah tomorrow, right? Hmm. Okay. So convolution. So did you guys start start doing some questions from the textbooks as we discussed in the last video? Convolution, or I mean, how are you experiencing with the convolution topic? Is it okay, or are you facing some kind of difficulty?
A little bit difficulty.
Yeah. Could you tell me like which questions you are facing difficulty with, or like what is the difficulty part that you are seeing? Like, is it with getting the intuition or solving the problem, or like where exactly are you feeling the difficulty?
It is necessary that t
Mm-hmm.
converted to tau, like xt as we written as xt.
Okay. So let me just revise that one more time and then take the specific question that you're pointing out. Mm, మ్, ఇక్కడే కూర్చొని అసైన్మెంట్స్ చేయాలి.
Excuse me, ma'am.
ఎస్ ముత్తుకృష్ణ.
Uh, ma'am, regarding the question in quiz one, that asymmetric and
We
symmetric.
are doing the re-evaluation. So yeah, that is sent to the team. We'll update you soon regarding that. Okay. Yeah.
Yes, ma'am, sure. And ma'am, I have one doubt in graded assignment week two.
Graded assignment week 2. Okay. So can we discuss that at the end of this session? Because it's
Yes,
from the
ma'am, sure.
back. Yeah. So
Yes, ma'am.
yeah, just to give some again. So last week Satyam asked like what are these LTI systems and how is the convolution came in the first place. So remember LTI system, L means linear, the system should be linear, T means time invariant. Okay, and yeah, Ti means time invariant. So any system that is both linear and time invariant is called an LTI system. We saw some examples in our last live session on systems which are linear and on systems which are time invariant. So any system that satisfies both this linear property and also the time invariant property is called as an LTI system. And a point to be noted is every LTI system is characterized by an impulse response. And what is this impulse response? So, impulse response usually is something when you pass the impulse direct delta function, which we also called unit impulse. So, when you pass this impulse into an LTI system, which you denote by maybe F, the output that you receive is called impulse response. Okay, which we denote by H of t. Okay, for example, suppose your given LTI system is maybe what can you tell me some example of an LTI system? Take y of t, or which you can also say some f of x of t, is x of t plus t naught. So clearly this system is an LTI system. This system is both linear and also time invariant. You can verify that. Okay, so this is an LTI system. And now what is the impulse response of this specific LTI system? So when you pass delta of t as the input to the signal, the output that you receive, which is f of delta of t, is nothing but delta of t plus t naught, would be your impulse response, which we denote it by h of t. So h of t is known as the impulse response of an LTI system, and every LTI system is characterized by something known as the impulse response. Okay. Um, Sorry for this, but let me charge my iPad. Mm, all right. Okay. So h of t is known as the impulse response of the system, and we saw like what is an impulse response, and every linear time invariant system is characterized by this impulse response, and the impulse response is nothing but the output of the LTI system when an unit impulse is transmitted into the LTI system. Okay, now so once you know the impulse response, once you know h of t, you can as well find the output of an LTI system when x of t is transmitted. So once you know h of t, you can as well find the output of x of t when output when x of t is transmitted through this LTI system. In other words, if you remember from our last assignments, x of t can also be written as minus infinity to infinity x of t, x of tau, del of t minus tau d tau, right? So from our previous assignments, if you remember, like I think week 4 assignment, we solved this problem, right? That integral minus infinity to infinity x of tau del of t minus tau is simply x of t. In other words, in plain English, what this means is x of t can be written as integral over some train of delta functions multiplied by this function x of tau. Okay, so x of t can be written as the sum over some x of tau multiplied with this impulse functions. Now what we do is, so let's try to analyze when this x of t is transmitted through an LTI system. So when this LTI system, which has the transform f, when x of t is transmitted, remember h of t is the response of the LTI system when the function delta t is transmitted. Okay, so what is the output? So the output that you see is, so x of t can be written as minus infinity to infinity x of tau del of t minus tau d tau. So when this is transmitted through the LTI system, the response, the output is f of x of t, which is f of integral minus infinity to infinity x of tau del of t minus tau d tau. Since f is a linear map, it is linear in integration, so it can be taken inside. So this is f of x of tau del of t minus tau d tau. So this can also be written as integral minus infinity to infinity. So this can also be written as x of t del of t minus tau d tau. And f, remember f is acting in the tau domain, so this is minus infinity to infinity x of t f of del of t minus tau d tau. I think I again broke the proof somewhere. This is the reason maybe it's better for me to carry notes. Okay, I think f is the transform that is being applied on the impulse. So this is x of tau f of d tau, and what kind of at the end gives you is integral minus infinity to infinity x of tau h of t minus tau d tau. So this is something what we define as the convolution of the two signals x of and h of t. In other words, if h of t is the impulse response of an LTI system, that is when you pass del of t into the LTI system, the output that you see, if this is h of t, then when you pass x of t into the LTI system, the output that you tend to see is x of t convoluted with the function h of t. So I mean, you guys don't need to remember this proof and all, but the whole idea is, every LTI system is characterized by the impulse function and an impulse response with it. So h of t is called the impulse response. Impulse response is something that when you pass del of t as the input to the LTI system, the output that you see is the impulse response. And once you know the impulse response for any other input that you transmit over this LTI system, the output that you tend to see is x of t convoluted with h of t. And this convolution takes the form x of t convoluted with h of t is of the form minus infinity to infinity x of tau h of t minus tau d tau. Okay, so this is it. So this is where we are getting the convolution operator from. So for any system to analyze, in order for you to analyze any system, suppose you have some system which is an LTI system. If you want to analyze this system, in the sense if you transmit some input into this LTI system and if you want to analyze the output of this LTI system, you guys definitely need to learn this convolution operation, because the output of an LTI system is always the input convolved with the impulse response of the LTI system. Okay, so that is it with respect to this convolution operator. So to answer your question, is it necessary to change the tau and the t? It is necessary, Satyam, because y of t, which is convolution of x of t and h of t, is defined as integral minus infinity to infinity x of tau h of t minus tau d tau, and you are integrating across tau. So the output that you see here is dependent now on t. Okay, and where are you getting this from? You are getting this from the fact that any input signal can be written as integral over the train of the delta functions. Okay, since when you pass delta function into an LTI system, what you tend to see, the output of the impulse response is h. So the output when you pass this over an LTI system would be x of tau f of del of t minus tau d tau, and this would be minus infinity to infinity x of tau h of t minus tau d tau. Okay, so this is where your, this is equal to x of t. So this is where your change in the time domains is coming from. Okay, and it is necessary for the convolution operator that you do the shift in the times. So yeah, Satyam, please go ahead with the specific questions that you're having now.
Not a specific question,
Mm.
but in graded assignment week 5,
Mm.
last question, I think the options which are provided is not matching with correct answer. Could you check from your side?
Okay, so I, one second, I'll check that. So I'll just correct this proof before doing that. So this is acting in the time domain, remember, and the given system is an LTI system. So you can take this into the integration, and this is f of x of tau del of t minus tau d tau, uh, d tau. This happens because f is linear, correct? And this is also equal to integral minus infinity to infinity. So f is acting in the t domain, hence this is like a constant over here. So this, the t domain you can see only in the delta function, so this is like a constant for f, right? So this is like f of some a times x of t. Remember, for LTI systems, f of a times x of t, for any linear system, this is equal to a times f of x of t, right? For any system to be linear, we saw a times x1 of t plus b times x2 of t will give us an input a times y of t, y1 of t plus b times y2 of t. Since the system is linear and the system is acting in the t domain, this tau domain is like a constant to this f function, hence you can get x of tau outside, and this is simply f of del of t minus tau d tau. Okay, reason for these two steps is f is linear, and this is simply integral minus infinity to infinity x of tau, and f acting on the delta function. Remember, the impulse output is h function, and since it is time invariant, when you transmit del of t minus tau, the output also will be h of t minus tau, because the system is time invariant. Hence this is h of t minus tau d tau, and here the reason is f is time invariant. Okay, so this simply is defined as the convolution function x of t and h of t. Is that okay? So I'll just repeat it. So what we are telling is every linear time invariant system is characterized by this impulse response, and what we mean by impulse response of a LTI system is when you transmit del of t into this LTI system, the output that you tend to see is the impulse response of that system. Okay, now to analyze for any x of t, what is the output? You write x of t as the integral over the train of the impulse responses which we have seen in our earlier assignments. Okay, and now when you, so if I call the LTI transform as f, when you transmit x of t as the input into this LTI system, the output would be f of x of t, which is f of integral minus infinity to infinity x of tau del of t minus tau d tau. Now, recall this f is acting in the t domain, and hence the tau domain is like constant to this f function. And because f is linear, this integration can come out and f will go inside, and f of x of tau del of t minus tau d tau. And again, since f is linear, a is like a constant to this, so the output would be a times f of del of t minus tau, where my a, this I am calling as a. Okay, so the reasons for these two steps is f is linear. Now since f is time invariant, del of t into the function gives you h of t. Since it is time invariant, del of t minus t will give you the output h of t minus t. This we already know from the definition of the time invariance. Since again f is time invariant, we can write this as integral minus infinity to infinity x of tau h of t minus tau d tau. In other words, if h of t is the impulse response of the LTI system, then when you transmit x of t as the input to this LTI system, the output that you tend to see is this, which we are defining as the convolution operation between the signals x of t and h of t. Here is where exactly this convolution operator is being defined, and the definition is given as integral minus infinity to infinity x of tau h of t minus tau d tau. Okay, I hope at least yeah, I think I did a correct proof today. Yeah, please go ahead, Satyam, with the questions.
Graded assignment, last question.
Which graded assignment?
Week 5.
Can you tell me what the question is, if you don't mind?
I'm getting different answer, which was not matching with the options which are given.
Let me open the question first. I'm sorry. So the graded assignment, last question. Okay. So what is x of t mm, convoluted with del of t minus t naught, right? Okay. So let's try to do this. So definitions first. What is x of t? Remember, we also saw certain properties. X of t convoluted with h of t is same as h of t convoluted with x of t. In other words, like when you expand them, x of tau, h of t minus tau, d tau, integral minus infinity to infinity, h of tau, x of t minus tau d tau. Okay, so these two are equal. That is what this property is stating. Okay, just to recall. Okay, so let's try to solve this 10th question graded assignment week 5. So let's try to write this out. So what is this? Integral minus infinity to infinity x of tau del of y. So let me call this function as y of t. Okay, so what is x of t convoluted with y of t? Integral minus infinity to infinity x of tau y of t minus tau d tau. Now what is y of t minus tau? Integral minus infinity to infinity x of tau del of t minus tau minus t naught d tau. Correct? Now let me call Okay, so now what? So this can be written as integral minus infinity to infinity uh, x of t minus t naught del of t minus tau minus t naught d tau. Is that okay? You can verify that this is true because mm, what you can verify is x of uh, tau times del of minus tau plus t minus t naught is same as x of t minus t naught times del of minus tau plus t minus t naught. This is something that you can verify. Okay, just by using our previous properties you can verify that this is true. And once this is true, this can be written as x of t minus t naught integral minus infinity to infinity del of t minus tau minus t naught d tau, and this is 1 we know, so hence this would be x of t minus t naught. So it's matching with the answers, right? Just like if you remember this problem, x of minus infinity to infinity x of tau del of t minus tau d tau, this is x of t, correct? So how did we do this? So we do this by stating yeah, if you know this, just by replacing here in this problem integral minus t with t minus t naught, if you replace, so this is something that we already know, we have solved this multiple times, right? Even in your previous assignment this is their previous assignment question. Okay, so now if you replace t by t minus t naught, nothing changes, so this del of t minus t naught minus tau d tau is simply x of t minus t naught, right? And you could as well say from the previous property itself directly, even without doing these things, you know, from here onwards. Okay, so you know this, from this what you can state is this, so this is same as this, so this is just x of t minus t naught. Is that okay, Satyam?
Yes, ma'am. Yes, ma'am.
Yeah.
Ma'am, can you check my solution in the where from I make
Yeah,
mistake?
yeah, yeah, yeah. So can you send me your solution on email?
Yes, ma'am. Send it.
Yeah, you can send me, I'll check and reply back to you. Okay.
Ma'am, I already sent
Oh, you
from
already
morning.
sent me? Okay, okay. I'll check this after the live session. Or you can even tell me if others don't have any doubts. You can even tell me at the end of the live session. You can wait for 2 more minutes. I will look the email right away. Okay.
Okay, ma'am.
Yeah. So uh, Muthu Krishna, is he there or he left? Okay, he was asking some question in week 2. Okay, any other questions that you guys have? Yeah, Gayatri.
In quiz 1, what was the issue with question 1?
Okay, quiz 1, question 1. The problem was you can prove it to be both conjugate symmetric as well as conjugate asymmetric.
Okay.
So the given uh, uh, constraints as well as the given problem satisfies both symmetric and asymmetric nature.
Okay.
Hence, all 4 options are correct. So that was the problem. Hence, we do re-evaluation for this question and we give full marks. Whoever attempted both, like if anybody says that the signal is symmetric, and if for both answers, like we would like to give marks. Okay, so that re-evaluation we will do.
Okay. So what are the answers for that?
All 4 options are correct. So if it is conjugate symmetric, I think the answers are A and C. If it is conjugate asymmetric, I think the answers are B and D. So
Okay.
anyone who attempted to say either AC or BD will be given full marks, but partial marks will not be given, because symmetric, if you say the signal is conjugate symmetric, then the C option is also correct. If you say
Okay.
the signal is asymmetric, then the D option is also correct. So anybody who attempted to give either AC or BD will be given full marks. Okay.
Okay.
Any more questions you guys have?
Yes, ma'am. I have a doubt from week 5.
Mhm.
Basically, signal yt equal to dx by dt.
Mm.
Can you tell me this is invertible or not invertible?
This is not an invertible system. I think professor gave a nice example in the lecture course on this example. The reason behind it is, remember the definitions that we studied for the invertibility. So for a system to be invertible, so any system we call invertible if and only if two inputs do not give the same output. Okay, so this is one of the definitions that we studied. One of the definitions for invertibility is two inputs should not give you the same output. But here in this case, suppose x of t is some constant which is 2. So x of t is some signal which is defined like 2 everywhere. Okay, so this signal, when you try to find y of t, so this is dx of t by dt. When you differentiate a constant, what you get is 0. Likewise, suppose you take another x1 of t, let it be some 5. Even here your y1 of t is dx1 of t by dt, which is 0. So y of t equal to y1 of t for x of t not equal to x1 of t. So two inputs clearly has the same, like two inputs clearly contain the same output in this particular case when the output is the differentiator operator. And such systems can never be invertible, because suppose you are given y of t, what are invertible systems? So if you remember the picture, when you transmit x of t into some system, you get some output y of t. Suppose you can come up with maybe this is some f function. So suppose if you can convert this, suppose you can come up with some f inverse function such that by applying this inverse operator on the output function, if you get your original input function back, okay, then you say such systems are invertible. But here in this case, clearly you cannot come up with any f inverse function which can, which is f inverse of 0, which can clearly tell you whether the input system is 2 with, input system is for sure 2 or input system is for sure 5. So if you know only the knowledge on the output function 0, you do not know whether the input is 2 or the input is 5. So you cannot retrieve back your input here in this case. Hence the system is not an invertible system. Is that okay?
Yes, sir.
Yeah.
And ma'am, another question based on this.
Mm.
Yt equal to cos in bracket xt plus c.
Yeah, so y of t is equal to cos x of t plus c. Again, here in this case, Satyam, let x of t plus c equal to 2 pi, which is nothing but x of t is equal to 2 pi minus c. Okay, and let x1 of t is 4 pi minus c. Then y of t is cos 2 pi, which is 1, and here in this case y1 of t is cos 4 pi, which is 1. So clearly y of t is again equal to y1 of t for x of t not equal to x1 of t. So again, by looking at, if someone gave you y of t is equal to 1, you cannot come up with any inverse function which will tell you whether x of t equal to 2 pi minus c is transmitted or 4 pi minus c is transmitted. This you cannot differentiate by looking at the output. Hence, the system is not invertible. Is that okay?
Yes, ma'am. Okay.
Any other questions? Any more questions?
Can you explain BIPO again? Please don't give stable, unstable.
Uh, uh, Live sessions are available, right? Is it so? What is your specific doubt?
Question like why t equal to x t by 2?
Yeah,
This is BIPO stable or not?
stable or not? Is that the question?
BIPO is stable or not?
BIBO. Okay. So, what is BIBO stability? BIBO stability implies bounded input should always give you bounded output. What does that mean? Suppose x of t is bounded by some m1. This should imply y of t Am I writing the constraint correctly? I think I'm not writing the constraint correctly. Let me open the. Hmm. Okay. Um. Yeah. So suppose if mod x of t. So suppose if your input is bounded, if you can say that your output will definitely be bounded, then such systems are bibostable. Okay, for example, y of t is x of t by 2. We know that x of t is mod x of t is less than m1 for all t. So whatever the definition that I wrote here is correct only. So suppose if y of t is given as x of t by 2, this implies y of 2t is x of t, correct? Yeah. So now
Yes, ma'am.
y of 2t for all t mod is also less than m1, correct? Is that correct?
Yes, ma'am.
And let me call 2t is some t prime. For all t implies t belongs to minus infinity to plus infinity. So 2t equal to t prime implies t prime also lies in between minus infinity and plus infinity. Okay. So this in other words implies y of t prime is less than m1 for all t prime such that uh, or for all t prime belongs to minus infinity to infinity, or this is same as stating y of t is also less than m1 for all t. What this proved is, suppose mod x of t is less than m1 for all t implies y of t by 2 y of t equal to x of t by 2 is mod t. Mod is less than m1 for all t. Implies the given system is bibostable. Is that okay? So for any bounded input, if you get bounded output, then such systems are called bibostable. Okay.
Ma'am, if we put t equal to infinity, then xt goes infinity.
Why will xt go to infinity? No, right? Suppose if t is infinity, x of t by 2, x of t is less than m1 for all t, irrespective of t, whether t is infinity or whether t is minus infinity. X of t is always less than some m1. That is what we mean by the consideration. This is the assumption that we take. We are considering, like we are starting the system with bounded input. Xt can never become infinity. For any t, x of t can never become infinity. That's the assumption we take. That's what we mean by bounded input. The input is always bounded. It can never go to infinity. So suppose if you take the bounded input, now the question is, will the output be bounded? Okay. But good question, if you have something like y of t equal to x of t times t. Suppose if you have something like this, then if mod x of t less than m for all t, this need not imply that mod y of t, which is equal to, if you apply Cauchy-Schwarz, this is mod t mod x of t, and what you know is this is less than m, so this is less than or equal to mod t times m. Okay. And suppose, so this, you can never say that this is less than or equal to some constant, as t varies from minus infinity to infinity, because this is dependent on t. Okay, you can never make this is less than or equal to some constant, because as t becomes infinity, this whole thing becomes infinity. So in this example, the system is not bibostable. But something like this, you can definitely say bounded input will always give you bounded output. Hence, the system is bibostable. Is that okay?
Yes, ma'am. I got
Okay.
it.
Any questions? Any more questions? Yeah, if you guys have no more questions, I would like to wrap up today's session. And Satyam, you can stay for 2 more minutes so that I'll clarify your whatever you sent on the email. Let me open and see that. Okay, so why are the other sessions being scheduled during the same time as our session? Because technically things shouldn't be clashed with our sessions, so our sessions have fixed times. So Wednesdays 3 p.m. to 5 p.m. will not work because I'm a working person and I'm away on weekdays, so 3 to 5 cannot be done. But I can speak to the team and I'll try to ask them to shift their session, because our session has been during the same time ever since the course started. So this is something that I will discuss with them. Okay. All right. So I'm writing to with the last question in the graded assignment. I mean, no options. Okay, let me see what you tried. Hmm, something wrong you did here, man. What did you do here? So this is not even the convolution that you took over here, right? Hmm. Could you explain it to me, like what you tried to do here?
Ma'am, from starting.
Hmm. So what is the first step? You consider t equal to tau. What does
Yes, ma'am.
that mean, considering t equal to tau?
Then put in tau in place of t in delta function, and in next line shift from t.
You cannot do that, right? Like, what is your convolution operator? Don't be confused with the operator, Satyam. So, what is the convolution operator? So, convolution operator is defined something like, so suppose if you have x of t convoluted with h of t, you are not replacing anything with tau. So, this is the operator that is defined like this. Okay, so suppose if you have x of t function defined like this, so x of tau is nothing but the same x of t function, so you don't need to do anything. So this is like you just have to act with the way like what it is given in the definition, so nothing more to do about it. But okay, continue. So I see. mm, I'm just trying to write it in this thing. Okay, so not possible. Okay. So yeah, so the first step is not correct. Okay. I think the problem that you're trying to experience here is because that you did something wrong with your first step. You're not replacing t equal to tau in the convolution operator. Convolution operator is something different, which I think it's better for you to understand more clearly on it and look through it more carefully. It's not just replacing t with tau. Okay, it's more than that. I think that itself, failed your attempt. You tried to replace tau with t, and then you did something over here. Like, what exactly did you do here
Which
in the
line?
second step? In the second step,
Uh, shift by t and take minus comma.
uh, take minus convolution. Uh, I don't know. Your steps doesn't seem right. So these are not the valid ways of doing it. I think the best way to do or go about it is, suppose x of t, and this is as what I told, previously. Try to call this function as y of t and then proceed. I think that your initial steps itself fail, like they are not correct. Okay,
Okay.
just look through the convolution operator more carefully. Try to understand it in a more better way so that things will be more clear to you. Okay.
Okay.
Yeah, thanks. Shall we end the session?
Sure.
Yeah, thank you for letting me know regarding the live session. I'll talk to the team. This cannot happen because ours
Ma'am,
was during the
this
same time
session
since
was
beginning.
passed away. This was 10th July session.
Which session?
Previous session 10th July.
Okay, only 10th July session got clashed, huh?
Yes, ma'am.
Okay, so they cannot do that. So that's the problem with the math team. Our session is already, been scheduled for 8 to 10, and they cannot happen their session during the same time. So if that's happening, you should talk with the math guys, not with our guys. Ours is fixed time till the end of this course. I cannot change the timings of the course. Okay.
Okay.
Yeah. Muthu Krishna, do you have any questions? I'm about to end the session. If you have any specific question, we can talk about it. Like you were telling me about something regarding week 2, right? So, what is your specific question?
Yeah, yes, ma'am. Yeah. So in week 2, graded assignment, ma'am.
Week 2 graded assignment, which question is that? Can you tell me?
So 1 minute. Think.
But this was long back, right? Like,
Yes, ma'am. I just saw the question. I didn't check again after that, so I missed it.
okay, so which question?
Yes, ma'am. Question 4, ma'am.
Yeah, which of the points are true about phasors? Is that
Yes,
the
ma'am. So,
question? Hmm.
yes, ma'am. So in this question, the last option, is it correct or wrong?
It's correct, right? Unit magnitude phasor is called a complex sinusoid. So, what is a phasor? So, phasor is something that can be represented in r e power j theta form. So, this is called a phasor. And what is a complex sinusoid? Complex sinusoid is cos theta plus j sine theta. Is a complex sinusoid function. So unit magnitude phasor, or you take any complex functions like xr of t plus jxi of t. Even in this case, you want your magnitude to be, or this yeah, but this statement is correct statement. Unit magnitude phasor is called a complex sinusoid. I think that is also available in your lecture notes if I am correct. So yeah, that's there.
Yes, ma'am. But the complex sinusoid is little more than unit magnitude phasor, right? It isn't necessarily should be a unit
It
magnitude, right?
actually depends on like how you would like to call it. I mean, if it depends on the course. Certain people actually tell it is more than that, but certain people teach it to be like this. So it actually depends on the way the course was being taught. But in our course, I think the complex sinusoid was explained as cos theta plus j sin theta form, and that complex sinusoid, whatever is explained in the course, which is given as a cos theta plus j sin theta, that has unit magnitude. So it's a unit magnitude phasor. So at
Okay.
least, yeah, at least if you, I mean, yeah, I understand if you had not, checked that option correct, you you would try ways to argue with me on, telling like maybe this isn't true. But at least with respect to the course that we are having, I think in this course it was taught like that. So yeah, that was picked from your
Yes,
lecture notes. Yeah.
yes, ma'am. Yeah. Even in lecture, actually, the professor skipped that portion. Actually, the
Okay.
slide.
Okay.
I mean,
But you don't need to worry about it so much, Muthu Krishna, if you have
yeah, yes,
done
ma'am.
all
I
your
just need to
questions
clarify.
correctly. Yeah. I mean, it actually depends on the course. If somebody had told you complex sinusoid is much more than, like cos theta plus j sin theta form, I think then you can think about other things. But I think at this level, this is okay.
Okay.
Okay. Yeah.
Mm,
The reason
yes,
why
ma'am.
we gave you that question is also the reason, is one of the reasons is this, that you would like to map these two pictures properly. But I think that's okay. If you do or don't do properly that question, I think that's okay, provided you have done other parts well. Okay. So
Yes,
it
ma'am.
doesn't affect you much.
Yeah, yeah, yes, ma'am. Is it correct to say every complex sinusoid has a unit magnitude?
It actually depends on the course. If somebody teaches you, so at times people tend to teach every complex sinusoid signal can be represented as xr of t plus, and the magnitude, if and the magnitude of the complex function will be given as, if somebody gave you that the function is a complex sinusoid, I think you can definitely say that this magnitude would be equal to 1. Okay, because in that case, the way you find the phase theta is tan inverse of xi of t by xr of t. The reason why you are computing phase in this fashion is you are considering your xr of t as cos theta and your xi of t as sin theta, right? And that is
Yeah,
where,
yes, ma'am.
when you divide these things, tan theta is showing up as xi of t by xr of t, and theta is tan inverse xi of t by xr of t, correct?
Yes, ma'am.
So when you call your theta to be this angle, then definitely your signals should also be in this form, right? And when the signals are in this form, the magnitude is 1. So it's a unit magnitude signal. Yeah.
Ma'am, but when we take the ratio, the magnitude part will get cancelled, right? Even if it isn't one unit magnitude.
So you're telling me, so this m cos theta, yeah, in general, it could be the case, but at least with respect to the this course is concerned, you can consider. I mean, it's not much of an issue, man. If you want to consider it unit magnitude, if you don't want to consider it,
Yes,
you
ma'am.
can
Just
consider
for
it to be general.
clarification, because
Yeah, yeah. There's a
in
certain things
EC
you can
I
just Google
remember.
and you can learn. Like you don't need to do much. This you don't need to make
Yes,
much deal out of it. So they're just some.
yeah, yes, ma'am. Just for clarification
Yeah,
and more,
yeah.
wider
Yeah,
view. Because
I
as per that,
agree
I
with your
googled it
statement
also.
that complex sinusoids are more general than like quarter unit magnitude signals. But
Yes.
the idea of giving you that question is to make you try to map it to the cos theta and j sin theta form. If it is
Yes,
going
ma'am.
away that from that thing, you can like ignore whatever we told, and you can consider whatever you are believing. Okay.
Yes, ma'am. Sure.
Yeah, if you're very
And
particular with
ma'am,
your marks, then we can think about it. But
no,
yeah,
no, no,
yeah,
no. It's just a point.
yeah. Okay.
And ma'am,
Gayatri,
are you
yeah.
in Discourse?
Huh?
Are you in Discourse, ma'am?
Discourse, I don't know because the team didn't teach me about discourse, so I'm not very sure of those things. I think somebody else also pointed out in other live sessions to log in this discourse and all, but the team never told me. But you can email me if you have any doubts, okay?
Yes, ma'am. Sure.
Yeah,
And,
so
and then, do we have a separate YouTube channel for where the live sessions will be
yeah, the
available?
live
Or
sessions are being uploaded in the portal. If you go to the contents of the course, I think in the course content front, somewhere live sessions, Google Sheet link is uploaded where they're uploading the live sessions. You can ask your friends, and yeah, they are being uploaded in the portal. You can check with your friends.
yes, ma'am. Sure.
Okay.
Yes. Thank
Gayatri,
you.
do you have
It
any
is there
specific
in
question?
no, no, it is there in the BS Electronics YouTube channel directly. Muthukrishna.
Okay. Okay.
Yes, ma'am. Yeah, sure.
They
Uh,
are not. They have not created a separate playlist or anything right now.
No, I think they uploaded a sheet in your portal, Gayatri.
Okay, but I'm
Yes,
just
ma'am. In important
So,
links.
yeah, in the important links, under the section important links, there is this link to the live session.
oh,
So, in
I see. Okay,
sheet, they are uploading all the YouTube links. Okay, you
okay,
can
okay,
check that. Mm.
okay. Last session's link is not there.
I will tell the team to upload last sessions and this session link. Okay.
Okay.
yeah, yes, ma'am.
Yeah, thanks. Gayatri, do you have any specific question? I see you joining back again.
No, no. Right now, no.
Okay, yeah, I would like to end the session then. Thanks, guys. Bye.
Thanks a lot.
Thank you.
Thank you, ma'am.
Yeah, bye.